Welcome to Constellations, a podcast from Kratos. My name is John Gilroy, and I'll be your moderator. In today's episode, we are joined by Dr. Siamak Hesar, CEO of Kayhan Space, a company focused on spaceflight intelligence, automated space safety, and collision avoidance. Today, we will discuss how building a safer orbital environment depends on shared data, intelligent automation, and global cooperation to prevent collisions and ensure space remains sustainable for the next generation of missions. You ready to go? Okay.
That's right.
Dr. Hesar, you have emphasized the limits of siloed operational data in collision prediction. So what is meant by siloed operational data, and how can it be addressed?
Thanks, John, for the question. And first of all, thanks so much for having me. This is fun. Let's look at the problem first. So as the number of satellites that are being launched into Earth's orbit increase, so do the number and the variety of the operators that operate those satellites. And by variety, what I mean is the sophistication of those satellite operators that actually operate their missions, right? So on one end of the spectrum, you have companies with very sophisticated systems, automated systems such as Starlink, that they are operating 8,000 plus satellites in LEO orbital environment seamlessly. On the other side of the spectrum, you have operators that don't even have a flight dynamics engineer on board on the staff to ensure that their satellites are safe or they are not posing risk to other people. So what has happened in the past decade and a half or 2 decades is that we have obviously, the commercial space industry has grown tremendously, and we are all fond of that. However, we have gotten to a point that we have a lot of the smaller and medium-sized operator that they have information about their satellites that are necessary for the safety of the overall space environment. However, those are not being shared with other operators. So that is really what I mean by siloed data ecosystem. And I can go into details of that if you are interested.
Yeah, I'm just interested in gaps here, So what gap do you see in how operators manage collision risks?
Yeah, one of the big gaps in when it comes to spaceflight safety and coordination is the fact that, and it's very simple, and that is that the operators do not share their planned maneuvers with each other, by and large. Again, I like to go, and I'm gonna be referring to Starlink throughout this podcast quite a bit because in my opinion they are obviously the largest operator in orbit, but also they are doing a lot of the processes well. So in a way, they are a model. But when operators don't share their planned maneuvers, in other words, my best analogy is like assume you're, imagine you're driving on the road and you want to turn left in the traffic and you don't turn on your turn signal and you just turn, right? So that turn signal is sharing planned, future maneuver plans that is going to result in changing your trajectory in a future time. And no one else in the world other than that particular operator that's planning to perform that maneuver or change of trajectory knows about the existence of that plan. Even, the U.S. government doesn't know it because they're tracking as things happen, right? So you can have cases that there could be a conjunction event that we predict. And by the way, when we say conjunction, is a potential collision. It's a probabilistic event. That's why we call it conjunction. So when there could be a potential conjunction that we are tracking, but because we are not aware that one of the operators is going to perform maneuver, that might not be there. The other side of the coin is even more worrying because if we are not tracking a conjunction and suddenly an operator performs a maneuver that no one is aware of it, last minute there's a conjunction. So that is one significant step that every operator can take to share their planned ephemeris and maneuver to make sure people around them know basically which direction they're going to turn.
You've talked a lot about the importance of ephemeris sharing as orbital traffic increases. First, please explain to our listeners what ephemeris is, and then maybe discuss some of the barriers to sharing high fidelity ephemerides among operators and how they can be overcome.
Sure. So when we say ephemeris in the space world, what we mean is basically a time series of position and velocity of a satellite that is flying in space in its orbit, right? And obviously, there are a lot of different standards. The most widely used standards is the CCSDS Consultative Committee in Space Data Systems. If I remember that correctly, CCSDS standards that we have OEM, OCM, OPM standards that a lot of satellite operators are familiar with these. But at the end of the day, what we mean by ephemeris or ephemerides is that they are a time series of position and velocity, or it's also called a state of a satellite that is in orbit, and also the prediction of the operator about their spacecraft, right? That it's going to be in the next few hours, in the next day, in the next 3 days. This is the orbit that I'm going to fly. And you can immediately see how important that is.
No, so I guess it's a table of celestial position, so you can have an idea of where something's going to be.
Absolutely. So, and it is one of the most important things when we data types that when we talk about space traffic coordination, because if you don't know where something is going to be, then you cannot coordinate, right? And by definition, space traffic coordination happens in the future, right? Because we want to coordinate our actions in the future time, and we do want to ensure that operators do share their ephemeris with each other. And going back to earlier question, the most important piece of information in those ephemeris files is the planned maneuvers that is included in those ephemeris files that tells everyone else, hey, I'm planning to perform this orbit raising maneuver, and I'm going to be higher altitude than what you see now. And as a result, everybody be aware of it.
Dr. Hesar, I think there's a lot of sources of data out there. It seems that data fusion is at the heart of situation awareness. So how do you bring together orbital data from different sources, government, commercial sensors, and operator telemetry to create this unified operating picture?
Very good question. So, yeah, and we have heard a lot about data fusion. I guess, there's a lot of literature on this. There's a lot of research, but I guess for the purpose of this conversation, I'd rather focus on what we are doing at Kayhan Space. And in that, what I see the role of Kayhan Space is a data aggregator in the space industry. And as such, we have basically are working very hard and coordinating with different sources of data to ensure that we are able to pull data from different sources to have a better picture of what is happening in space and space environment compared to the case that if those data sources are siloed, as we talked about. So that data source can be tracking data that the U.S. Space Government, the U.S. Space Command, the U.S. government is doing through 18 Space Defense Squadron and the Space Surveillance Network. That is one source of data. The other source of data is GPS-based tracking data from our own customers, satellite operators, as well as other operators that do share their GPS-based ephemeris, both how they have flown, but also their predicted ephemeris, even more importantly, with the public. As well as there are a lot of commercially available data sets that, or commercial companies that track objects in space, and we work with them to pull their data. And I think that is as the space becomes more congested and more, the number of objects increase, for us being able to track objects using different types and phenomenologies of data sources is very important, because certain things might not be very visible with one particular type of data.
Dr. Hesar, earlier in our conversation, you used the word conjunction. Let's bring that up again here. AI and ML are increasingly applied in conjunction and anomaly detection. Could you explain how AI is used to sift through fused data and improve collision prediction accuracy?
Very good question. Yeah. Obviously, we are in the AI world these days, and there has been, especially in the past few years, it's been mind-boggling for me personally to see the significant amount of growth and improvement in artificial intelligence side, and specifically when we talk about large language models. A lot of people, when they talk about AI, we always combine them, AI, ML, but obviously there's a big difference between machine learning algorithms, the statistical-based machine learning algorithms versus these large language models that are kind of the next level of artificial intelligence. And I definitely am in favor of utilizing LLMs in space applications. However, that application needs to be used in a correct way. And what I mean by that is a lot of the things we do in space environment, and the work that we do with flight operations, with space traffic coordination, with conjunction assessment, those are all very nuanced physics-based models that we have very accurate models about it. We have very accurate models about the governing forces that act on an object in space and how it is going to evolve and how it's going to move into orbit. So it's like you don't want to ask AI or LLM to tell you what's 2 + 2. I mean, the answer it might come back is 4.1, right? So in cases like that, that's a very simplified example, I guess, but in cases like that, when we are talking about equations of motion and physics and physical forces that act on objects, there's not really place for AI or LLM to add any value. However, when we now deal with a system level or kind of a mega system of system level process where there are very complex constraints. Let's say we have a constellation, we want to make optimization of that constellation for whatever purpose. There are all these real world constraints around how to achieve that optimal goal. Then in those complex environments, obviously using LLMs is very useful. You mentioned in your question anomaly detection. That's a very good use case for LLMs to teach them about what is the quote unquote normal behavior of an object for purpose of national security or even commercial purposes. And then if there is certain anomalous action from that object, then the LLM can quickly detect that.
If you go to a trade show and listen to a panel of AI experts, they inevitably talk about your phrase, using it in the correct way. And this leads to privacy. So privacy or proprietary concerns often inhibit data sharing. So are there privacy techniques that can help, especially when operators may not want to reveal their orbital details? That's where it gets difficult, isn't it?
Absolutely. And this is not something we should take it lightly. I mean, we are always talk about data sharing, the importance of it, and how people need to cooperate. But there are certain areas, for example, national security reasons, or in the regions of war zones, and not just government assets, but also commercial assets that are providing certain important data sets for government and national security purposes. There are definitely serious concerns in terms of sharing their precise ephemeris, where they are going to be, and how they're going to change their trajectory. So let's put that aside for a second. So that is obviously common sense, national security reasons. That's something that I don't think should be shared widely. But I would say the vast majority of concerns from commercial and purely commercial satellite operators about sharing their ephemeris and maneuver plans and such is not well founded. And the reason I'm saying is that because at the end of the day, we have, I talked about commercial data providers. That these are, that there are a lot of companies that they have radars, telescopes, that they track objects in LEO and GEO and, MEO environment. And at the end of the day, we all see these objects. We know where they are. We know what they're doing. So by not sharing your ephemeris, you're not really hiding anything. And again, I'm only focusing on purely commercial activities. And the downside, however, is bigger, which is that it is by not sharing those information, that information and those data sets, we are putting everyone at risk. So definitely there is concern. And when it comes to conjunction assessment and space flight safety, a lot of people don't realize that the amount of data that we require to make an informed decision about a conjunction and avoid a potential collision is very minimal, actually. So, for instance, when I'm talking about sharing maneuver plans, I want to be very clear. I'm not talking about, hey, go ahead and share your propulsion technology, your, I don't know, like your, what is your power system and, how you maintain your attitude, all that stuff. None of that. What I'm saying is that basically the thrust vector in which that you are going to perform that maneuver that is going to result in changing of the trajectory. So the amount of data that we can share for spaceflight safety reason is very minimal. And, there are definitely ways that we can, keep them secret for the purpose of, making sure that people are comfortable with sharing those.
Earlier you facetiously mentioned that AI would tell you 2 + 2 is 4.1. Everyone knows it's 4.2, but
Yes.
but the problem is that it's with AI and regular intelligence too. When combining data from multiple sources, differences in data calculations occur. How do you manage uncertainty and ensure operators do not receive conflicting information?
This is a very good question, and it is at the heart of data fusion. When people talk about data fusion, what really people mean is that what is the best way of combining different sources of data and different types of data to get the best information out of those data sets. So you are correct. There are different data sets, there are different types. Not every data is generated the same. There's going to be large and uncertainties on some of them. Some are going to be more precise than the others. For example, GPS data is very precise compared to ground tracking, optical systems or radar systems. However, as long as the data set is accompanied by information about their precision level, or the other side of the coin of the precision is obviously uncertainty, or lack of precision or uncertainty. As long as it comes with that information or information about the biases on the sensor, that enough information for a system to be able to process that data properly. We have there's a lot of different systems. They are known mostly as orbit determination filtering systems that basically they collect different sources of data based on the information they receive. They are able to estimate and utilize different sources of data commensurately to their accompanying uncertainty. And even if those information are not supplied, we can still figure out the level of uncertainty or biases and such by using what's called calibration satellites. That in fact we do this work we support U.S. government in evaluating a lot of data sets for them, because we don't own sensors, so we are kind of the third party unbiased source of truth, if you will. And we use, quote unquote, truth trajectories or calibration satellite trajectories to calibrate the data sets that might not come with that type of information.
When you talk about AI and data, the topic of scale always comes up. And if we look at projections of satellites next 3 years, I guess we talk about scale, and scale is important for a lot of things. So as constellations scale into tens of thousands of satellites, collision management, I guess, has to scale too. So could you walk us through the challenge of handling real-time operations and potentially hundreds or thousands of conjunction events simultaneously? How many can you juggle, Doctor? A lot.
Yeah. Turns out people can actually juggle a lot because, again, I want to go back to Starlink. That's a very good real world example of a constellation that really, in the matter of few months, from having 0 satellite, they became the largest satellite operator in the world. And today, if I'm not mistaken, they have on the order of more than 8,000 operational satellites, the Starlink constellation, and how is that done? Through automation. That there is absolutely, obviously, no way to be able to manually operate all those satellites. So automation is key, but actually, I want to kind of change the focus of question a little bit and talk about the fact that the number of objects, we always talk about, the number of objects and satellites going to space and increasing and congestion is increasing. Obviously, that is the problem. But the bigger problem, and again, Starlink is a good example, is not that we don't have the capability of operating many large number of satellites, right? Clearly we do. Starlink is doing it every single day. The problem again comes back to lack of communication. So, for instance, what Starlink cannot do is if another operator that is in their vicinity or in their neighborhood, if they do something that is not communicated with Starlink, and again, if they perform a maneuver that is not communicated and they suddenly show up in front of one of their satellites, then that is something that Starlink cannot control. So again, I guess at the crux of all this, when you go to the root of this, yes, there are technology solution is rather, I don't want to say it is trivial, but it is doable. Automation is doable. The human factor and the factor that there are all these different companies, operators that we need to get them on the same page that, hey, you need to all share this type of information with each other. That is the part that concerns me. And, when we talk about problems with scaling, those are the things that really come to my mind that we need to resolve those issues.
A lot of startup companies talk about innovation and really it has to be applied somewhere. So let's talk about maybe applied innovation here. So how do you see commercial innovation helping shape future norms for orbital operations?
Yeah, we have come a very long way. A very short amount of time. Every day when I look at different ideas and the companies that are starting a space venture and they are pursuing different ideas that I've never thought about before. That's always interesting. The innovation is always a great fuel for moving forward in an industry. So there are, and again, space is a vast topic. Industry is it has a lot of different verticals. My expertise when it comes to space is about space operations, satellite tracking, and space flight safety. And in that area, there are very specific parts that innovation can really help us. And in that, better sensors, better tracking. That is something that we can all get a great advantage of. Tracking of smaller objects because we are only tracking 40,000 objects or so consistently, and there's on the order of 1 million debris objects in space around the Earth.
Wow.
So we are not even tracking like a very small percentage of it, right? There is a lot of innovation in building more resilient satellites. So in other words, putting kind of bumpers, if you will, right, in your car, that in case you hit a piece of debris, I mean, some objects are large enough, there's no protection against them, but you can actually make your satellite more resilient against some of these smaller pieces of debris that we are never going to be able to see, so that your satellite doesn't disintegrate, for instance, right, or doesn't break apart, so it creates more debris of its own. Maneuverability is another big topic, and it can be controversial. Obviously, it is more expensive for operators to have a maneuverable satellite, but to me, from my perspective, that is someone that's concerned about the spaceflight safety. If you are building a satellite that is not maneuverable and you're launching it into space, you're basically adding another debris. I mean, yes, you can communicate to that satellite, but it's not going to be able to change its course in case there is a conjunction with another piece of debris, let's say, right? Now, I want to be clear. Some satellites and satellite operators, in fact, we have also demonstrated this, that you can change your attitude profile and basically perform what's called differential drag. So using force of drag to change your trajectory. So that, to me, that's a maneuverability capability. Automation and the correct use of large language models, I think, is going to be another big breakthrough in space industry in the coming years.
I've been taking notes of this conversation. I got thousands of satellites, millions of pieces of debris. So let's try to project what's going to happen in the future. So looking ahead, what is your vision for AI-driven orbital management? Is it possible to see a world where maybe even autonomous satellite coordination becomes routine?
I actually don't think we have any other choice. I mean, when we are talking about thousands of satellites visiting by each other and coordinating, again, I like analogies, and my best analogy again is autonomous cars, right? Autonomous driving. And the first thing when you drive, as a human driver or an autonomous driver, is that informing other drivers around you, informing the traffic about what you are going to do. So that's why we have turn signals. That's why we have brake lights, to inform other drivers around you that what are your intentions. So obviously, with autonomous cars, a lot of these communication could happen through through sensors, through connections between different cars. Same can happen in space, and in a way, you can, and the way I think about the space problem is a large node, right? So is a large network. And if you think of all these operators as a node of this network, now you have thousands of these nodes. So for each one of these nodes to now start having a connection with another node, suddenly you are going to have a very complex system, and it's almost not doable. So, and that's kind of how I see the role of Kayhan, is that as a kind of arbiter in between all these operators, it's a platform, and that is why we built SatCat, which is it actually has a lot of free for public capabilities that everybody can enjoy, satcat.com. But we have several, greater than basically more than 30 satellite operators on SatCat that are coordinating each other. And we have, in fact, been able to enable autonomous coordination between different satellite operators via that platform. So having a central node through which the different operators talk to each other, I think that's how this process can scale properly.
No, that's fascinating. I think you have given our listeners a better understanding of sharing data, automation, and AI. I'd like to thank our guest, Dr. Siamak Hesar from Kayhan Space CEO. Thank you.
Thank you so much. Appreciate the time.